So now we want to continue with the next subtopic, which is the linearized velocity potential equation. So what we have already gone through earlier, the velocity potential equation. So we have already gone through step by step in terms of getting the velocity potential equation that being used for the compressible flow subsonics over airfoil. Okay, with regard to the linearized velocity potential equation, we want to consider the two-dimensional irrotational isentropic flow over the body. This is the airfoil shown in figure 2. So this is imagine there is an airfoil in a free stream of uniform flow and perturbed flow, right? So you can see there's a free stream velocity, and we have a velocity component V over there, and component of velocity U and small v, right? Okay, so the body is immersed in a uniform flow, right, with velocity V infinity oriented in the X direction. So we have this X direction and Y direction vertically. So at an arbitrary point P, so imagine there's an arbitrary point P in the flow field, the velocity V with the X and Y components given by U and small v respectively. All right. So let us now visualize the velocity V as the sum of the uniform flow velocity plus some extra increments in the velocity. Okay. So for example, the X component of the velocity U, X component of the velocity U, which is given here in figure 2, can be visualized as the V infinity plus an increment in velocity, either positive or negative. And similarly, in the Y component of velocity V can be visualized as a simple increment itself, right? So because the uniform flow has a zero component in the Y direction, you can see here there's no Y component of the of Y in the Y direction, zero component in the Y direction. So these increments, these small increments are called perturbations, right? And we know that the U component of the velocity, which is equal to the free stream velocity V infinity plus U cap, U with a small hat over there, and where V, small v is also equal to only the small v with a small cap. So where this U and V with the caps are called the perturbation velocity, right? So why there is no V infinity for the small v component? Because as we said that there is no zero, it is a zero component in the Y direction. Right, that's the reason. So this is where this small box of expression for U and V being expressed. So basically these are what we call as the perturbation velocity. The U cap and V cap are called the perturbation velocities. So these perturbation velocities are not necessarily small, right? So indeed, they can be quite large in the stagnation region in front of the blunt nose of the body. So if we imagine that right in front of the nose of the airfoil over there, so the perturbation velocity may be having a different values, right? So in the same vein, because of the V, the velocity itself is equal to the change in the velocity potential, as we have already defined earlier. We can define a perturbation velocity potential as a pi hat, such that pi equal to V, V stream, velocity V stream, velocity at the free stream in the X direction plus the velocity potential perturbation, perturbation velocity potential pi. Okay, so at the same time we know already um, the perturbation velocity velocity potential pi in the x direction and in the y direction is equal to the perturbation velocity at u and v. Okay? Hence, we have this expression, right? So I believe I do not have to read out all of this. So we imagine that we can obtain all of this expression. 1, 2, 3, 4, 5 expression over there. So substituting the above definitions that what we have already found in the previous slide into equation 12, the equation of velocity potential equation, and multiplying it by the speed of sound squared, right? We will obtain this expression where it is equal to 0, right? This is called equation 14, which is called the perturbation velocity potential equation, right? Earlier, equation 12 is only velocity potential equation, but this is the perturbation velocity potential equation. So it is precisely the same equation as equation 12, except that it is expressed in terms of the pi hat, where it instead of the only pi, right? This is a perturbation velocity potential instead of just velocity potential. However, it is still a non-linear equation. So to obtain a better physical insight in some of our subsequent discussion, let us recast equation 14, this equation, in terms of the perturbation velocities. So what happened is that from the definition of the perturbation velocity potential, pi hat, given earlier in equation 14, can be written as the components of velocity potential, perturbation velocity for u as well as for v, right? Okay. So this is, we call it as the equation 14a. Okay? And from energy equation, we can then express the component as equation 15. All right. What we will do next is basically substituting equation 15 into equation 14. So you want to use this expression of the speed of sound squared over gamma minus 1 plus this component, right, into 14a. So you will then get the expression for equation 16, which is being expressed over here. You have the component of the Mach number as well for the free stream. So equation 16 that we have already obtained in the previous slide is still exact for irrotational isentropic flow. And note that the left hand side of equation 16, okay, the left hand side, which is this expression, okay, of equation 16, is linear, but the right hand side is non-linear. What we have on the right hand side over here, from these three lines, are non-linear. Okay. Also, we have to keep in our mind that the size of the perturbations for u and v can be large or small. Equation 16 holds for both cases. Let us now limit our considerations to small perturbations. So we assume it is only small perturbations, and that is assuming that the body in figure 2 is a slender body at a small angle of attack. In such case, the perturbation velocity u and v will be small in comparison with the free stream velocity. Therefore, right, so we know that the perturbation velocity u, perturbation velocity v, with respect to the velocity, free stream velocity are very small. We have this less than 1, and at the same time, for the component of the u perturbation squared as well as v perturbation squared with respect to the free stream velocity are very, very small. There are 3 less than over there, which we said is very, very small. All right. So keep in mind that the products of the perturbation velocity u and v with their derivatives are also very small. So if we examine again equation 16 and compare like terms, coefficient, or of like derivatives on the left as well as the right hand side of equation 16, we will find out that for the range of Mach number free stream between 0 to 0.8 or more than 1.2, the magnitude of this expression, okay, the Mach number in terms of the free stream velocity as well as the perturbation velocity u until the end is small in comparison with the magnitude of this expression. Thus, we can ignore the former term, right? So, to continue, for the range of Mach number less than 5, because if it is more than 5, it is hypersonic. So we want to consider less than Mach number 5, right? So this expression is small in comparison with the small changes, the changes for velocity perturbation for V in the y direction, so we can ignore the former term as well. Also, this expression is approximately 0. Okay, so with the above order of magnitude comparisons, equation 16 that which we had 3 lines just now can be reduced to only this, which is equal to 0, right? Or in terms of the perturbation velocity potential, so this is in terms of the perturbation velocity u and v, the component, right? U and v in x and y direction. So if you want to convert it into perturbation velocity potential, right? So we can also express that in equation number 18. All right. So what happened is that we examine again equation 18. It is actually a linear partial differential equation, right? And therefore is inherently simpler to solve than its parent equation, equation 16, because we have already looked and reduced it significantly to become equation 18, which is quite simpler, simpler in terms of the terminology over there, the unknowns and the knowns over there. So, however, we have paid a price for this simplicity. Okay, because the equation 18 is no longer exact, because we have reduced significantly the other components. It is only an approximation to the physics of the flow. Okay, it's because we are making assumptions where we want to do design of aerodynamic shapes, so we have to try to reduce. There is a paid, there is a cost when you do a lot of assumptions. All right. So due to the assumptions made in obtaining equation 18, okay, it is reasonably valid, but not exact for the following combined situation. Number one is that small perturbation that is for thin bodies at small angle of attack. Okay, there's a more. This is the situations as well as subsonic and supersonic Mach numbers, right? So in contrast, this equation 18 is not valid for thick body. So you cannot use it for thick body. We can only use it for thin body at small angle of attack with subsonic and supersonic Mach number. And it is also not valid for large angles of attack. Moreover, it cannot be used for transonic flow. So that's why we only limit it up till 0.3 to 0.8 and more than 1.2 just now. Okay. So the transonic flow from 0.8 to 1.2 Mach number or Mach number more than 5 is not being used. We cannot use it for these ranges of Mach numbers. All right. So those are the limitations. And to continue, we are now interested in solving equation 18 in order to obtain the pressure distribution along the surface of a slender body. So since we are now dealing with approximate equations, it is consistent to obtain a linearized expression for the pressure coefficient, which is an expression that is approximate to the same degree as equation 18, but which is extremely simple and convenient to use. So the linearized pressure coefficient, Cp, right, can be derived as follows. So first, we want to recall the definition of pressure coefficient, Cp, where Cp equal to the P pressure minus the free stream pressure divided by Q infinity, Q free stream, which is actually the dynamic pressure. Q infinity over there is equal to half rho infinity times the velocity squared infinity. So which is equivalent to the dynamic pressure. So the dynamic pressure can be expressed in terms of the free stream Mach number as follows. So you can express the dynamic pressure components as equation 20 down here. And from the expression of the speed of sound for the free stream squared, which equal to the gamma times the pressure free stream divided by the density free stream. Hence, equation number 20 can now be rewritten as expression equation 21, where you know that V over A is actually the Mach number. So now you already expressing the dynamic pressure in terms of the Mach number. So we can now substitute back equation 21, right, the dynamic pressure, okay, into equation 19, which is we know the equation that we use for the pressure coefficient. So we will have this equation 22, Cp equal to 2 over the gamma times the Mach number squared free stream times the pressure divided by pressure free stream minus 1. Okay, so we call it as equation 22. By the way, equation 22 is simply an alternate form of the pressure coefficient, so which is expressed in terms of the free stream Mach number. It is still an exact representation of the definition of the coefficient of pressure, Cp. To obtain a linearized form of the pressure coefficient, recall that we are dealing with an adiabatic flow of a calorically perfect gas. Hence, we can now write down the expression for the temperature plus the half velocity squared over Cp, which is equal to the free stream temperature plus V velocity free stream squared over 2Cp. And this is, we call it as equation number 23. So recalling back, whereby the coefficient of pressure Cp equal to the gamma times the gas constant R divided by gamma minus 1, equation 23 can be written as this. T minus T infinity will be equal to this expression. So we replace basically the Cp components from equation 23 over there. The Cp component we replace by gamma R over gamma minus 1, you will get expression of equation 24. We also know that the speed of sound at the free stream, which is equal to the square root of the gamma RT infinity, equation 24 can now be rewritten to be equation number 25. Okay. So in terms of the perturbation velocities, right? So the V squared, velocity squared equal to, this is in the X component and this is in the Y component. So we know already earlier, equation number 25 can be rewritten as equation 26. So basically, you are replacing V squared there, right? In terms of this expression. So we will now obtain equation 26. So we know already, since the flow is isentropic, the pressure ratio P over P infinity, P free stream, which is equal to the temperature over temperature free stream times the gamma and divided by gamma minus 1. This equation 26 can now become expression of equation 27. And the pressure ratio, P over P infinity, right? So you can rewrite that in equation 27. So equation 27 that we have already found is still an exact expression. So however, let us now assume that the perturbations are small. So the perturbation velocity U divided by the free stream velocity, which is less than 1, and where the perturbation velocity U squared over free stream velocity squared, which is much less, very smaller than 1, and at the same time perturbation velocity V to the squared over free stream velocity squared are also the same, which is very small than 1. So in this case, equation 27 is of the form of this. So we have where this eta is small. So we can say that this is another expression for this pressure ratio. Okay, because of this condition, which is very small, so the terms are insignificant. From the binomial expansion, we can neglecting higher order terms. Equation 28 can becomes this expression as equation 29. And by comparing equation 27, we have equation 27 here, which is this expression down here, right? To equation 29, and we can express the equation 27 as equation 30, right? So that's how we want to try to further simplify and replacing with the known value, right? Substituting equation 30 into the expression for CP, the pressure coefficient. So we want to put back in CP, where equation 22, we then obtain these expressions where this pressure coefficient CP equal to the minus sign of the 2 times the perturbation velocity U over free stream velocity V, minus perturbation velocity U squared plus perturbation velocity V squared over free stream velocity squared, right? So that is we call as equation 31. All right. So since we know that the perturbation velocity squared over V squared free stream and perturbation velocity V squared over V squared free stream are very small, very small than 1. So the equation 31 itself becomes only CP equal to minus 2 times perturbation velocity U over the free stream velocity, right? So because of this, this component are very small, less than 1. So equation 32 is what we call it as the linearized form for the pressure coefficient, and it is valid only for small perturbations. Right? So equation 32 also is consistent with the linearized perturbation velocity potential equation, which we have already derived in equation 18 earlier. And note that the simplicity of equation number 32 is look very simple over there. It depends only on the x component of the velocity perturbation of u, right? So no component for v, because v is considered to be very, very small. All right. So to round out our discussion, okay, to summarize on the basics of the linearized equation. So we are talking about linearized velocity potential equation. We note that any solution to equation 18 must satisfy the usual boundary conditions at infinity and at the body surface. So at infinity, clearly the velocity potential pi with small perturbation, perturbation of velocity potential is constant, and that is the small the u, the perturbation velocity component u and velocity perturbation component velocity component v equal to 0. Okay, so at the body, the flow tangency condition holds, and let theta be the angle between the tangent to the surface and the free stream. So basically, at the surface, the boundary conditions is obtained where tangent theta equal to v over u. If you refer back at figure 2 earlier, right? And you will also see that the perturbation velocity v is over free stream velocity plus the perturbation velocity u. So this is the component. Okay, so because what we already obtained earlier in the figure number 2, which is actually an exact expression for the flow tangency conditions at the body surface. So if you want to look back at figure 2, you can now appreciate where is tangent theta, right? A simpler approximate expression for equation 33 that we have already obtained here, okay, which is consistent with the linearized theory. It can be obtained by noting that for small perturbation, where perturbation velocity component u, which is much less than the free stream velocity, hence equation 33, right? So we can rearrange it as, because u, perturbation velocity u is much less than free stream velocity, so we have perturbation velocity v equal to the free stream velocity tangent theta, and you can then express it in terms of the perturbation potential velocity pi in the y direction equal to the free stream velocity of tangent theta. This is equation number 34, where equation 34 is basically an approximate expression for the flow tangency condition at the body surface with accuracy of the same order of equation 18 that we found before the break, okay, as well as the equation 32. All right. So with that, basically we have already looked into the theoretical part, and the theoretical part in terms of the two-dimensional compressible flow subsonic over the airfoil. So we have already expressed the velocity potential equation, and we also look into the linearized velocity potential equation. So next, basically, we are going to look at the corrections in terms of the approach by Prandtl-Glauert compressibility correction. And then we will also look next week in terms of the improved compressibility corrections. We will also touch upon critical Mach number, the area rule, and finally we will summarize the topic on two-dimensional compressible flow subsonic over the airfoil.